This section 3.5 will be about algebra of functions. Algebra of functions will be the topic that addresses operations with functions such as addition, subtraction, division, multiplication. But one thing about when you are performing these operations and composition. So we have addition, subtraction, multiplication, division, and composition of functions. But the one thing about when you're performing these operations, if you have two functions with two different domain, you may find yourself in a position to determine what would be the resulted domain for the function that you find. For example, you have two functions, f and g. You add them to create one function. How the domain of the two different functions combine to give you the domain of the one function. So that's what we're going to look at in this topic. So that's why we need to talk about the domain of a function before performing in any operations of the functions. So the domain of a function will depend on the type of function you have. Like when you have the domain of a graph, it's easy to read the graph from left to right and give the domain and the range. But when you have the equation of the function, you're going to make sure that you identify the type of function you have and then find out what conditions on the x values that will always give you the existence of a y value. So for example, if you have a function f of x equals 2x minus 5, a function like this, there is no x value that you would plug into this expression that will not give you an output for y. So any x value you plug into this function will give you a y value. So that makes this function exist. That makes the conclusion that this function exists for any x value. So the domain will be all real numbers. But say that you take that function, f of x equals the square root of x. Well, we need to remember in the set of real numbers, you can only take the square root of numbers that are positive. If the number is not positive, the square root will not be a real number. It will be a complex number. So this function will exist as a real number function, or I would say this function will exist only if x would be greater or equal to 0. That's how you would be able to calculate the square root of that x. It has to be greater than 0. But x greater than 0, if you take the number line, that's 0, negative infinity, positive infinity. Greater than 0 would be from 0, including 0, to everything on the right of 0. So that means this part of the real number will not, any x on this part of the real number will not have a y value. So this function will not exist on the left side of the set of real numbers because you can only take the square root of positive numbers. That explains why the domain for this function f of x equals x squared is conditioned based on whether x is greater than 0 or not, greater or equal to 0 or not. So that's the restriction that applies to the type of function based on what the expression of the function is to find the domain. Now, that's why I'm going to show you these rules to allow you to identify what to do whenever you have different type of function. And by definition, the domain is the set of all x values for which the function exists. In other terms, the set of all values for which a y value can be found. Just like we took the example for f of x equals square root of x, a y value cannot be found if x is less than 0. So then under this condition, a x that is less than 0 will not be part of the domain of x. And so here are some examples. For example, first, if a function is a polynomial function, for a polynomial function, the domain will be all real numbers, always. For example, f of x equals 3x squared minus 8x plus 4. The domain is all real numbers. All real numbers means takes numbers from negative infinity to positive infinity. All real numbers. So another example here, that's another polynomial function. Domain is all real numbers. This example here, all real numbers. If you don't have a denominator that will make it not exist for a certain value, or you have a radical or other type of function will have different type of condition of existence, then you would, if it's just a regular polynomial function, any function like this, or f of x equals 2x, that's a polynomial. It's a monomial, but also it's part of the class of polynomial. The domain will be all real numbers, or from negative infinity to positive infinity. So that's the first type of function we see. Now, if we have another type of function like g of x equals the square root of p of x. Well, p is a polynomial function. P is a polynomial function. Well, in this case, you need to set the condition that the expression inside of the radical must be greater or equal to 0. Otherwise, you won't be able to calculate the square root. So that's a condition. For example, if I have f of x equals square root of x minus 1, the domain will be x minus 1 greater or equal to 0, or x greater or equal to 1, which will be from 1 to positive infinity. That will be our domain. Take only values that are greater than 1. That's just a quick example. What if you have a denominator? You have f of x equals this. G of x equals p of x over q of x, where p and q are polynomial functions. Well, p, it's on top. It's not going to be a problem. The only problem is you cannot have 0 in denominator. Just like you can't divide by 0. So the fact that you know that you cannot divide by 0, you always want to know what x value that can make the denominator equal 0, and remove them from the set of values that are part of the domain, because 0 in denominator will not give you a real number. So you set the condition that the bottom of the expression should not be 0. That's when you have a denominator, the bottom is not going to be 0. And you need to find all the x values that make it equal 0 to exclude them from the set of real numbers, and the rest will be part of your domain. Here's another situation. G of x equals the square root of G of x equals the square root of P of x over Q of x. Well, for this one, you need two conditions because you have something inside of the radical that you want to be always positive, and then you have something in the denominator that you want to be different from zero, not equal zero. So you have two conditions. P of x that is inside of the radical, you want it to be always positive, and then Q of x that is in the denominator, you want it to be not equal zero. So you're gonna solve and find and that's why I put and. And those two conditions should intersect. Wherever they intersect would be your domain. And another condition is if the top expression G of x equals P of x divided by the square root of Q of x, well, P of x is okay. It's not inside of the radical. We have nothing. It's just a polynomial. Just like polynomials domain are all real numbers, P is fine because it's on top. But if it's in the denominator, then you would set the condition. Now let's take a look at the denominator. Not only the denominator has Q of x, but the Q of x in denominator is affected by a radical. So you need to make sure that the inside of the radical is positive. And then the whole square root of something is not zero. But you know the square root of zero is what? Zero. So you want the inside expression Q of x not to be zero here. You want that Q of x to be positive, but also greater than zero because it's in denominator. So you're not taking the case where it equals zero, because if it equals zero, then you would have something that does not define it as a real number. So knowing all these conditions, we are ready to be able to find the domain of a function if the expression is given. Our first example is this. So you have this function f of z equals the square root of 4z plus 24 over z minus 9. Now we're looking for the domain. So the expression inside of the radical should be greater than 0. So 4z minus 20 plus 24 should be greater or equal to 0, and the expression in the denominator, z minus 9, should not be 0. We're going to solve both of them and find out where these intersect. So let me solve this inequality. I'm going to subtract 24 on both sides. Got 4z is greater or equal to negative 24. We divide by 4. We get z that is greater or equal to negative 6. Let's solve this. We want z to be not 9 if you add 9 on both sides. Now, yes, we want z to be greater than 0. I mean, z to be greater than or equal to negative 6. As you're going up, you're going to pass through 9. You want to avoid 9 because 9 will create another situation that you don't want to be in. So let me show you that on the number line. On the number line, if this is 0, negative 6 will be on this on the left side of 0. We okay with negative 6. And then I'm gonna take negative 9 over here. So negative 9, we're not okay with it. We're gonna keep open on it. That's not negative 9, positive 9. And then everything from negative 6 to negative 9 is okay. And everything after positive 9, everything after positive 9 is also okay. So basically, the domain will be including negative 6 to 9 union 9 to infinity. So that's a domain. Domain of this function will be bracket on -6 because it's included, to +9. We're not including 9 because we don't want it in this domain. Union 9 to infinity. That's a domain for this particular function. Let's see another function here. For this one, it's easy because they just give me the radical. So the expression inside of the radical should be always positive. So 2x minus 8 should be greater or equal to 0. If we add 8 on both sides, we're going to have 2x that is greater or equal to 8. If we divide by 2, we would have x is greater or equal to 4. On the number line, what this would look like, that's 0. 4 would be on the right, and then everything on the right of 4 can be part of the domain, since the only problem is we don't want to take things that would make the expression negative. And obviously, if you take anything that is on the other side of 4, it would make the expression inside of the radical negative, which will not be which you will not be able to evaluate if if you want to stay in the set of real numbers. Okay, so that means the domain here, domain of f of x, domain of f of x here is from 4 included to infinity. From 4 to infinity. Next example is the same type. We want the expression inside to be positive. We're going to subtract 15 on both sides. Negative x is greater or equal to negative 15. If we divide by -1 both sides, we would have to switch the inequality. X is less than 15. On the number line, let's see how it looks. If this is 0, and negative 15 will be on the left because it's negative. I mean, positive 15 will be on the right because it's positive. '15 will be on the right, it's positive, and it's included. And then x elements that are in the domain, you need to be less than 15, so that be on the left side of 15 to be the domain. On the left side, you go all the way to infinity, negative infinity. So the domain will be from negative infinity to positive 15, but that is included. So that's your domain for, that's the domain for this function. Next example here, we have the denominator that is, we have x plus 6 over x squared minus 100. So we're going to make sure that the denominator is not 0. Denominator is not 0. So x squared minus 100 cannot be 0. Cannot be 0. So we can factor this as x minus 10, x plus 10 cannot be 0. So that means we're going to want each factor not to be 0. So we don't want x plus x minus 10 to be 0, and we don't want x plus 10 to be 0. So that means x cannot be positive 10, and x cannot be negative 10. These are the only values that will mess up the function. Other thing will be fine. On the number line, how do you remove these? So that's 0. Negative 10 will be here, not included, because it will mess up the function. In denominator would be 0. and then that's positive 10. Also, we don't want it here because it will mess up that function if we put it in the if you replace it in the function. So the parts that we can utilize will be over here, negative infinity to negative 10, over here, 10 to negative 10 to positive 10, and then over here from positive 10 to positive infinity, which makes the domain those three pieces of the number line that excludes only the negative 10 and the positive 10. So that is from negative infinity to negative 10, union from negative 10 to positive 10, union from 10 to positive infinity. And you can see we put parentheses for positive and negative 10 because they're not included in the domain, what otherwise you would just take the number line, the whole number line, which would be all real numbers. I have some few more examples that we want to practice. We're gonna go quick on them. Those are not part of the guided notes. You can copy them if you want, but I just want to go over these in case problems like this appear on your homework. Here's this one. This one has a denominator, so we want it to be not equal 0. So that's going to be x squared plus 7x plus 12. We want it to be not equal 0. We can factor this, or you can use quadratic formula to solve it, to find the factors. So to find the values for which x equals 0, the values of x that make this expression equal 0. So you can solve this equation equals 0 and then set x and the x values not equal because you want them not to be these values to exclude them. So two values that multiply to give you 12 and add to give you 7, that's 4 and 3. So that's x plus 4, x plus 3. We want it to be not 0. So we want x plus 4 not to be 0. And we want x plus 3 also not to be 0. Meaning x cannot be negative 4 and x cannot be negative 3. So basically on the number line, how this would be seen as, if this is 0, that would be negative 3, negative 3 here, and then negative 4. Both of them would be on the left side. We don't want them. We don't want them here because they will mess up the bottom to make it equal 0. And then the fraction will not exist with the bottom being 0. So everything else works. Everything else works. So we have values from negative infinity to negative 4, from negative 4 to negative 3, and from negative 3 to positive infinity. That makes the domain from negative infinity to negative 4, union negative 4 to negative 3, union negative 3 to positive infinity. That will be the domain for that function. Next example here, we have a radical on top and the denominator, so we're going to need to create two conditions. The expression inside of the radical cannot be 0 and cannot be, can be 0, but cannot be less than 0. Should be greater or equal to 0. And we also don't want the bottom to be 0. So x squared, x cubed minus x, we don't want it to be 0. So this one, x should be greater or equal to 6. And then we want x times x squared minus 1 to be not 0. Meaning that x cannot be 0. X squared minus 1 cannot be 0. So that's x cannot be plus or minus 1. So on the number line, we can see how this looks. You can see how this looks on the number line. So let's see how this looks on the number line. So we have 0 here. I always like to put 0 because it defines the sides of the number line that we're going to use. We had x is greater than 6. So let me put 6 over here. That's 6. And it's included, right? And then everything on the right. But also we need to think about excluding +1 and -1. But +1 here, that's 1. And then that's -1 right here. And then 0. So we should exclude 0. We should exclude -1. We should exclude 1 based on the conditions set here with the bottom of the equation. But we are lucky enough to have those numbers already excluded from the first condition, right? They were already excluded because if I take the numbers that are only greater than 6, -1, 0, and 1 are not included in this set. So we don't have to worry about the bottom condition anymore if we focus on the first one. But it's not always going to be like that, because if it was x minus x plus 6, if it was an equation like square root minus -x plus 6 to on top, then it would be this side of the number line that you would have considered as your domain. It would have been this side here. It would have been this side if you had a function. The top function would be like that. If the top function was that, then your it would be this for the blue part for your domain, and then -1, 1, 0 would have been needed to be excluded. Okay, so you need to pay attention to that. And in this case, your domain would have been -1, negative infinity to -1 would have been. It would have been. It's not that now. I'm just showing if you had this function, what the domain would have been. So it would have been from negative infinity to -1, union from -1 to 0, because you need to exclude all those values, and union from 0 to 1, union from 1 to 6, and then bracket on 6 because you can include 6. That's what it would have been if this function was that. But since it's x plus 6, then it's not that. It's not the blue. It's not the blue. It's only going to be from 6 to infinity. It's much simpler than what it would have been if it was the function -x plus 6. Now let's look at the next example here. This example gives me a denominator, a complicated denominator, for which you need to make sure you analyze and make sure you set the right conditions. You have two things: the part that is inside of the radical, and then the whole thing that you don't want, the whole bottom, you don't want to be 0. So the two conditions are going to be 2x minus 6. We don't want it to be less than 0. So we want it to be greater or equal to 0. And we also don't want the whole entire bottom to be 0. So we want 2 minus 3 square root of 2x minus 6. We want it to be not 0. So this one is that you can add 6 on both sides. 2x is greater than or equal to 6. We divide by 2. X is greater or equal to 3. And then we're going to solve this. Let's subtract 2 on both sides. Negative 3 square root of 2x minus 6, we want it to be not equal negative 2. If we divide by negative 3 on both sides, square root of 2x minus 6, we want it not to be 2/3. If we square both sides, 2x minus 6, we want it to be not 4/9. 4/9. And then we can add 6 on both sides. 2x not equal to 4 plus 9, 4/9 plus 6. 4/9 plus 6 is 54 plus 4, 58. 58. 54 plus 4/9. That's 58/9. And then divide by, so that's 2x equals 58, not equals to 58/9. And then if we divide by 2, meaning multiply by 1/2, we got x that is not equal to 29/9. Let's see what it looks on the number line. That is 0. That is 0, and then positive 3 here. We would have no issue including 3. And then to positive infinity. But now let's see where we would have the 29. 29 is 29/9 is 3.22. So it will be somewhere after the 3, 29/9, which we want to exclude, because it would mess up the denominator. If x equals 29/9, it will make the whole denominator equal 0, which we don't want to happen. So that said, we're going to exclude this. Everything else is okay. So I would take from here to here, and from 29 to not 29/9 to infinity. So that is the domain is from 3 bracket, because it's included, from 3 to 29/9. We're not including this because we want to exclude it. Union 29/9 to infinity. That will be your domain. Think that solves all type of domain we want to go over. Now the next step would be now other type of operations over function, type of operation that are the sum. So if I have f and g of two functions, of n g, two functions, the sum would be f plus g, which is defined by f plus g of x is f of x plus g of x. That's the sum. We go to this page to write down the rules. Subtraction. The subtraction will be, if I have f and g, will be f minus g. which is f minus g of x equals f of x minus g of x. Multiplication is f times g, or fg, which is fg of x, f of x times g of x. Division. F over g is f divided by g of x, which is f of x divided by g of x, under the condition that g of x cannot be 0. We already know that, because if it's 0, then f over g of x would not exist. We also have the composition, which looks like the multiplication, but it's not. The composition is f composition. You see, that's not a multiplication. G of x, which means f replace x by g of x. F substitute g into f of x. F composition g of x is substituting g of x by x into g of x, into f of x. Again, composition, f composition g of x is subbing g of x into f of x every time you see x. And g composition f of x would be the same thing, but the backwards. That's g substituting f of x. Substituting f of x into g of x every time you see x. Backward. Okay, so that understand, we can go ahead and do an example. We have f of x equals x squared minus 14x, and g of x is x plus 14. We want to find first a f plus g of x. F plus g of x. That is f of x plus g of x. We had f of x that is x squared minus 14x plus g of x that is x plus 14. We don't need the parentheses really, so that's x squared minus 14x plus x plus 14. Combine like terms, x squared minus 13x plus 14. So that's g f plus g of x. F plus g of x is x squared minus 13x plus 14. Because this is a polynomial function, the domain will be all real numbers, which means from negative infinity to positive infinity. Let's see what f minus g of x is. F minus g of x would be f of x minus g of x. Same thing here. G of x is, f of x is x squared minus 14x. G of x is x minus 14. We can drop the parentheses by distributing that negative sign, -1 here inside to change the sign of everything. So we have x squared minus 14x minus x plus 14. So that is x squared minus 15x plus 14. X squared minus 15x plus 14. And the domain, since this is a polynomial, will be the same as the previous domain. Two different functions can have the same domain as long as they are the same family of functions. So that's x squared, that's a domain is from negative infinity to positive infinity. Our next question is C. We want to find the product of f and g. So C f times g of x, that is f of x times g of x. So that is x squared minus 14x times x plus 14. Well, that's a FOIL. We're going to FOIL this. X squared times x, that's x to the third. X squared times 14, that's 14x. Negative 14x times x, that's negative 14x squared. Negative 14x times 14, that's 196, negative 196x. So we can combine like terms if any. That's 14. Let me go through it again to make sure. That's x squared times x. That's negative. That x squared times x. That's x cubed. X squared times 14. That's 14x squared. And then we have x squared times x. X squared times x. That's x cubed. X squared times 14. That's positive 14x squared. We got negative 14 times x, and negative 14x times x, negative 14x squared. And we got negative 14 times positive 14, that's negative 196x. So we have negative 14x, positive 14x, negative 14x, that's 0, x squared, x cubed, minus 196x. Okay? So that is x cubed minus 196x. And the domain, it's a polynomial function. All polynomial function will have a domain that is all real numbers. And in D, we have f over g of x, that is f of x over g of x, that is replacing x squared minus 14x over x plus 14, under the condition that x plus 14 should be not 0, should not be 0. So x cannot be negative 14, which will give me a domain that is from negative infinity to negative 14, union from negative 14 to positive infinity. So the answers are f of x, f over g of x, that is x cubed minus 14x over x plus 14. X cannot be negative 14, so then the domain will be negative infinity to negative 14 union negative 14 to infinity. Our next example will be a similar function, but it includes some complicated parts of it. But we have the same formulas that we can apply for each function. We have g of x is negative 3 plus square root of x, and h of x is negative 2x plus 14. Now we want to find f of f plus g, f plus g plus h. We want to find g plus h, g minus h, g times h, and g divided by h. So let's start with g plus h of x. That is g of x plus h of x. So replace g of x by negative 3 plus square root of x. And then h of x by negative 2x plus 14. So that makes, we don't really need the parentheses. So negative 3 plus square root of x minus 2x plus 14. Combine, if we have like terms, we can combine negative 3 and 14. That's the only things that we can combine. So that's negative 2x plus square root of x plus 11. The domain will condition based on everything we have. We don't have a polynomial now, given that we have x inside of the radical, because we're not going to have this expression unless x is positive or equals 0. So your domain will be, this thing should be greater than or equal to 0, which will make the domain here of g plus h of x to be, that's 0 here. So include this. It will be everything on the right side of 0, which is this, from 0 to positive infinity. So that said, your domain for f g plus h will be from 0 included to positive infinity. Otherwise, numbers that are less than 0 would give you an expression that does not exist. So your g plus h of x is negative 2x plus square root of x plus 11 with a domain that is from 0 to positive infinity. So next question is B. This time they want me to calculate g minus h of x, which is g of x minus h of x. G of x is negative 3 plus square root of x, negative 3 plus square root of x minus h of x, that is negative 2x plus 14. That's negative 1 that will change the sign of everything inside. So then you're going to have negative 3 Yeah, I'm sorry that there was a call on my phone and I'm using my computer to record this. So that's what happened. So negative 3 plus square root of x, negative 1 here that would multiply everything and change the signs. So that is negative positive 2x, and minus 14. Combine like terms, negative 3 minus 14, that's negative 17, but we're going to put 2x plus the square root of x and minus 17. We know that the expression inside of the radical should be greater than 0, meaning that the domain will be from all the positive numbers for x, from 0 to positive numbers. And it includes 0. So that's why we put a bracket here, bracket, and then 0, comma, infinity. Next example here will be about composition of function. We talked about that earlier. If I have f composition of x, of g of x, that means f of g, f composition g of x is f of g of x. G composition f of x is plugging f of x into g of x every time you see x. Well, what if they want me to find f composition itself? F composition f of x. Well, that would be plugging in f of x into f of x. So every time I see x in f of x, I replace it by itself again. That's how you would calculate f composition f of x or g composition g of x. Depends on what they ask you. So that said, f of x is x squared minus 6x, and g of x is x plus 1. So if I'm calculating f composition g of x, f composition g of x, it means that every time I see x in f of x, I will replace it by g of x. That is, since g of x is x squared minus 6x, so that would be basically g of x squared minus 6 times g of x. Replacing x by g of x. So that would be x plus 1, which is g of x squared, minus 6 times x plus 1. Can leave it that like that, or you can expand it. To expand this, you're going to have to use FOIL for the first part. That would be x squared, FOIL, right? So that's x plus 1 squared, that is x plus 1 times x plus 1. FOIL this, x squared plus x plus another x plus 1. Combine that terms, makes it x squared plus 2x plus 1. And then this, you distribute negative 6. Negative 6x minus 6 x squared minus 4x minus 5 would be the simplified result, but you could have used this one. I think it would still give you this, you would still have your full credit, and that's why I write it in blue. You have your choice. Either you use the expanded expression, or the just replacing the g of x into f of x. The next question is to find g composition f of x. It's the same thing that we did, but backwards. G composition f of x is g replacing f of x in it. That means every time I see x in g of x, in g of x, I put f of x. G of x was x plus 1. So that would be f of x plus 1. What is f of x? X squared minus 6x plus 1. Well, that's f of x. And then plus 1 was the plus 1 from g of x. That is g composition f of x. What is f composition f of x? Well, we talked about it. F composition f of x would be replacing f into f of x every time I see x. So that is f of x. When we replace, that be f of x squared minus 6 times f of x. That was the formula for f of x. So then f of x was x squared minus 6x minus 6 times x squared minus 6x. If you want to expand it, there's a square right here. If you want to expand it, go on and do it. You would get, do it in blue because you don't have to. That'd be x4 minus 212 x cubed. I foiled this, but I'm going to do it quick. Plus 36x squared minus 6x squared plus 36x. Combine like terms, you get x4 minus 12x cubed plus 72x squared. Not 72x squared. That is plus 30x squared plus 36x. Next question, D. They want you to find G composition G of x. So G composition G of x is G of x. G of x, it means that you replace x by G of x in G of x. So that means given x, G of x is x plus 1, it's going to be G of x plus 1. Or just x plus 1 plus 1, right? G of x is x plus 1. So that's x plus 2. So G composition G of x is x plus 2. Next question here, they say find F composition G of negative 8. F composition G of negative 8. You have two ways you can find it. You can go back to F composition G, what you had, and plug in negative 8 to find it. Or you can just do F of G of negative 8. You will try to find G of negative 8 by plugging in negative 8 into G of x. Let me find it on the side here. G of negative 8 is negative 8 plus 1, which is negative 7. Replace it here. That's f of g of -8. We found it, -7 here. And then you calculate f of -7, which is -7 squared minus 6 times -7. So that is 49 plus 42. This is 97. 91. So we have f composition g of -8 is 91. We are also asked to find g composition f of -2. G composition f of -2 is g of f of -2. On the side, we can find f of -2, that is -2 squared minus 6 times -2. That is 4 plus 12, which is 16. Back to the equation now. That is g of 16. G of 16 is replacing 16 into g every time we see x. So that's 16 plus 1, which is 17. G composition f of -2 is 17.